Star Wars Day. May the Force be with you. We're back at the Iziko Planetarium, this time for a talk by Dr. Matthew Huber on asteroids, meteors, meteorites, and how they've shaped South Africa. After a quick photo op for the rover and Vader, it was into setting up orbitals, getting things going, and playing with the dome. The millions of asteroids flying over our heads.
Good afternoon. My name is Dr. Matthew Huber. I am going to be presenting to you this afternoon the real Star Wars, Meteorites, Meteors, and impact craters of South Africa. Before we start talking too much about this, let me introduce myself to you. I often get the question, where am I from? And that's a complicated story. I grew up in the United States, University of the Western Cape, and now I'm in Durban, working at the University of KwaZulu-Natal, and also the Planetary Science Institute in the United States. But you didn't come to hear about me. You came to hear about things going on in our solar system. So, let me ask you a couple of questions. First of all, can anyone tell me how many stars we have in our solar system? It's dark in here, so I have a hard time seeing you. Can anyone shout it out? One! Indeed, we have one star in the center of our solar system. I hope you all knew that, and you're just a little shy. Let me ask you another simple question that I think you all know. How many planets do we have?
8.
Does everyone agree? Some people think 8 and some people 9, but usually we agree that the solar system has 8 planets. We can name them from the Sun: Mercury, Venus, Earth, Mars. Those are the inner planets. Then the outer planets of Jupiter, Saturn, Uranus, and Neptune. Now, a little bit of a trickier question. How many dwarf planets do we have? We have at least one. Anybody have an idea?
4.
You're getting close there. We in fact have 5. Pluto is perhaps the most famous of those because it was originally thought to be a planet before we discovered a number of other objects in the outer solar system, Aries and Haumea and Mahe. But then in the inner solar system, in the main asteroid belt, we also have Ceres that orbits with the other asteroids and was the first object discovered in the asteroid belt. So we have 9 planets and 5 dwarf planets, but does anyone have a guess how many moons there are in the solar system?
5.
A lot is a very good answer. There are 423 moons that we've identified, and the planet with the most of those is Jupiter. Does anyone have a guess how many comets we might have in our solar system? Does anyone want to guess? Do you think we have 100 or 1,000 or 10,000? How many?
100.
We have 4,014 comets that have so far been identified. It's hard to say how many we actually have because a lot of the comets live far away from where telescopes can look at them, and they're very hard to spot. But you can start to see all of these glittering dots all over. Those are the present positions of the comets that we know about. One thing you'll notice that's different between the planets and the other objects, the planets tend to be in pretty well-behaved orbits around the sun, whereas the dwarf planets and the comets have orbits that are a little bit more irregular. So now let me ask you a really tricky question. How many asteroids do you think we have?
100? 10,000.
I heard 11,000, 10,000. 5,000. In fact, we've identified 1,446,950 asteroids. There's asteroids all over our solar system. Usually, when there's a diagram of the solar system, they'll draw a little belt and say, this is the asteroid belt where all of the asteroids live. But the truth is that the asteroids are all over the place. Can you see where Earth's orbit is there? I'm not sure that I can. Somewhere hiding in that cloud of asteroids, there's us. Every single day, our planet is whizzing past rocks that are of various sizes. Some of these asteroids are quite large, some are quite small, but we're constantly coming in contact with them. In fact, there's about 40,000 tons of material that fall to Earth from space every year. As the exploration of space has gotten more advanced, we've learned a lot more about asteroids than what we used to know. Almost all of these discoveries have happened within the last 20 years. Here we finally come to the orbit of Earth. In the inner solar system, it's almost a shooting gallery of rocks that are whizzing around, coming past us, and leaving pockmarks all across all of the rocky surfaces that we can observe. We've been able to learn a lot about these asteroids in recent years because we've been able to send probes that have made it not only all the way to the asteroids, but have also returned back to Earth. There's recently been the return of the OSIRIS-REx mission, which brought back samples of the asteroid Meteor that have never been seen before. But that's not the only way that we can get samples of these asteroids. We don't have to wait for a mission to go to them, because they sometimes come to us. Every night, if you're watching carefully, you'll see objects falling from the sky. You'll see them shoot past us, make these long streaks. Maybe you can make a wish on one of the shooting stars. Of course, they're not really shooting stars. This is the rocks and dust left over in most cases from the origin of the solar system. But that's not the only source of these meteorites and these shooting stars. Some of them have come from collisions that have occurred in the solar system and knocked things into our way. One of the other very large objects in the asteroid belt is the asteroid Vesta. Vesta is the largest of the asteroids that is not a planetesimal or dwarf planet. So Ceres is the largest, and Vesta is the second largest. We had a mission that went to visit Ceres and Vesta and learn more about it. It was called the Dawn mission. You can see here's Vesta, and here's planet Earth. The Dawn mission was launched in 2007 and spent about 6 years observing Vesta. Vesta was first discovered back in the 1800s, But up until the Dawn mission, we didn't have a very good picture of what Vesta looked like. This was the best we could do with the Hubble telescope before the Dawn mission arrived at Vesta. Once the mission did arrive, we got much better images of what it looked like. Now we can see all of the fine details of what Vesta looks like. It's covered in craters, but also has strange, long lines that stretch across the surface of the asteroid. And you notice on the bottom side of it, it doesn't make the spherical shape that we might expect from a large object, but instead looks like it has some kind of pimple sticking out of it. Now, because of this mission, we've been able to learn a lot about the interior of Vesta. In this diagram, we've cut away a section of the surface to see the interior. There's a metal core at the middle of it. But as we go up, we have 3 different compositions of the asteroid. Now, we already knew about these, at least we already suspected them, even before the Dawn mission went. Because we have 3 kinds of meteorites that are all related to each other. They're named Howardites, Eucrites, and Diogenites, but those names are hard to remember and hard to pronounce, so people usually just say H-E-T. So we could learn not only about the surface of Vesta, but even about the interior, and see where these different objects came from. Some from the near surface, some from deep inside the mantle of Vesta. Now let's come back to that little pimple that I mentioned on the south pole of Vesta. What that is, now on the left side you can see the image of what Vesta looks like if you were in a spacecraft looking out the window. But on the right side, what we've done is we've added some colors to that so that you can see which areas are high in the red and which areas are low in the blue, and get a better sense of the topography. And we see that big circle there, that's labeled Rhea Silvia. And Rhea Silvia is a gigantic impact crater. There was another asteroid that collided with Vesta and left behind that big crater. Not only did it make a big crater, it also launched a lot of material from the crater out into space. That's how we know about these Howardites, Eucrites, and Diogenites, because they were launched out by this particular impact basin. And we can find these here on Earth. And not only here on Earth, but here in South Africa. In August last year, on August 25th, in the Eastern Cape, there were some kids walking along the beach when they saw something funny was going on up in the sky and quickly pulled out the camera. What you can see there is a meteor shooting through the sky, breaking apart into various fragments. Each one of those pops is as a new part of the meteorite is melting and breaking apart from its neighbors. And then the lights go out. The lights don't go out because it's completely dissolved and disintegrated. It's just because it becomes too slow to be burning in the atmosphere. You see, when a meteor is traveling into our atmosphere, it starts off at speeds of 70,000 kilometers per hour, which is even faster than the taxi drivers drive on the N1. After this meteor fell, there was a young girl sitting under a tree, and she heard something hit the tree, and then she watched as a rock fell out of the tree. The rock that the individuals holding in their gloves on the left is that exact meteorite. After it was tested and analyzed, it was found that it was a Howardite meteorite. It traveled all the way from Vesta to the Earth. Now, this was not the first meteor to fall on South Africa. The first meteorite that was discovered was found in 1793 by James Sowerby. It was a pretty large meteorite. It started off 136 kilograms. You can see he liked it so much when he had his portrait painted, he included the meteorite on his desk. But you can also see that the original shape is a lot bigger than what it looks like now. That meteorite was cut into a lot of fragments and shared all over the world with various museums. Some of it's in Hungary, some is in Austria, a bit's gone to England. Even in a single museum, there's a lot of different fragments that have been collected. But the most interesting of those fragments is being housed in Russia right now. A portion of the meteorite was melted down and forged into this sword. In 1814, Napoleon Bonaparte was just defeated, and so in celebration of this sword was commissioned and given to Tsar Alexander I of Russia to celebrate peace in Europe. This is now sitting in St. Petersburg, Russia, and you can read the inscription. This iron, having fallen from the heavens, was upon his visit to England, presented by His Majesty Alexander, Emperor of all the Russians. We have other famous meteorites in South Africa. This was actually in Namibia. This is the Hoba meteorite, which is one of the largest meteorites in the world. You can see that this one's housed in an outdoor shrine. Generally, it's agreed that the reason for this is because it was too heavy for anyone to move to a museum. Those steps around it are not the crater that the meteorite made. It was buried when it was discovered. This one is about 100,000 kilograms. It's a lot larger than the Cape of Good Hope meteorite. Now, when we step up to larger meteors than this, we get to things that can be quite dangerous. And you'll notice these first ones that I'm showing are iron meteorites. But we also have rocky meteorites like those that came from Vesta. And when those pass through the atmosphere, they have a tendency to blow up in the atmosphere, which can have some interesting consequences. A little over a decade ago, in Chelyabinsk, Russia, this meteor fell through the sky. You can see how brightly that one burned. That one's estimated to have been about 24 million kilograms in size. And when it blew up, it sent a shockwave through the sky that wound up damaging about 3,000 buildings. A lot of people were injured, not by the shockwave, but because when they saw the flash in the sky, they walked over to the windows to see what had caused the flash. And that's about when the shockwave came and broke the glass. So almost all the injuries were a result of broken glass. We haven't had one of these fall over South Africa in recent memory. But we do have evidence that even bigger objects were falling on South Africa in the past. Near Pretoria, there's the Swang impact crater. We can estimate that the original size of this would have been a meteorite that was about 60 million kilograms. But this one hit more than 200,000 years ago. It made a crater that's about a kilometer in diameter. And this one is a crater that looks like a crater that you imagine. It's a perfect bowl shape. It looks like you could eat soup out of it. It has a nice, happy lake in the middle. And when it hit, it probably sent a shockwave in the surrounding area and knocked over some trees and scared some antelope, but otherwise didn't do too much damage. Now, to imagine what a 60 million kilogram asteroid would look like, we can think about this asteroid Dimorphos that was recently visited by the DART mission. And we can imagine that if it was about the size of one of the buildings underneath Table Mountain, that would be roughly the size of an asteroid that would be able to make a crater like the Swang crater near Pretoria. We can even model in a laboratory what this would look like. In a laboratory, we use a gun to fire a bullet at a prepared target. And when we do that, we can send objects flying at close to the speeds they would hit if it was impacting the Earth. And we can see what it does to a target. This will often make a crater that's quite similar to the craters that we observe in nature. And we can fairly easily start to make complicated diagrams where we model what's going on when these projectiles hit the Earth. The asteroid will strike the ground. It will bury itself to about the diameter of the impactor, and then it will essentially blow up. And when that happens, a lot of rocks get melted. A lot of rocks get blasted out into the sky, and a lot of rocks get broken. That's what we basically expect for any big impact. A lot of rocks melted and a lot of rocks broken. But the swing impact crater, in my mind, being only about a kilometer in diameter, I don't think it's all that big. And of course, it's more interesting to think about the nuances. So what if we had a really big impact? Not the building under Table Mountain, but Table Mountain as the impact. So let's estimate that Table Mountain, let's say it's roughly a kilometer tall and about 10 kilometers in area. That would make a pretty big impact. But I would rather a really big one, so let's double that. And double it again. And double it again. And let's add a few more for great measure. Once we get up to that size of impactor, that's approximately the size of the impactor that forms the Vredefort impact crater, which is not only the largest impact crater in South Africa, but the largest impact crater in the world. Now, we can't really simulate what that would do in a laboratory, because simulating that would be bad for anybody on Earth. So instead, we have to rely on computers to simulate this for us. So what we're looking at here is the preparation for a simulation of a gigantic impact. Now those numbers on the left, those are in kilometers. So we can see that that half circle up at the top is about 15 kilometers wide. That's our impactor. That's going to strike the surface of the Earth. It's going to move straight down, and that big rectangle that starts off at the 0 line, that represents the surface of the Earth. And going out, those numbers along the bottom, those are also in kilometers. That's going to show us how far out the material is damaged. Now you'll notice that we have a half circle here when we don't expect any asteroid to be in a half circle shape. That's just because this takes a lot of computer power to do, so we always cut everything in half, because the left side and right side will be the same. So you have to imagine that this is mirrored in order to get the full effect. Now the colors are going to change from blue to yellow, and that will show us an estimation of how much fracturing is happening in the rocks. Let's see what this looks like. Now you'll notice the time is going. This has been about 5 minutes from the time of the impact. So what we can see in this simulation, we see first of all that there's excavation, that this impactor comes down and excavates the material. This is the crater that it makes. You can see that it's 40 kilometers deep. 40 kilometers below the pre-impact surface. But that doesn't last for very long. Because then, just like if you threw a rock into water and you watched it splash back up, the rocks here actually behave like water and rise back up. And now you can see these poor rocks that started off living happily by themselves, went on a journey in less than 3 minutes that sent them 40 kilometers below the surface, and then back up again more than 20 kilometers above where they were before. It's only after that that they settled down. You can see that the rocks have been completely overturned. The landscape out to a humongous distance from the point of impact has been irreversibly changed. Now, we can see a pristine example of what this looks like by looking at the moon. We'll come back to South Africa in a moment. This is the Schrödinger crater on the moon. This is near the South Pole. And this one is about the same size as the Frederick crater. So we can see the crater rim on the outside, this outer edge of the circle. And we can see an inner ring, that's the inner peak ring. And we see all that flat material that's making the floor of this crater. That's all the material that's molten. When you have a crater that's this big, it can make a 3-kilometer thick sheet of molten material that cools down over a period of 1 million years after the impact. While it's cooling down, it makes these big fractures that tell us that there was still a lot of activity going on at this crater long after the actual impact event. Now we have other examples of craters that are almost this big on Earth. First, there's the crater that killed the dinosaurs. This one's buried under the Gulf of Mexico in the Yucatan Peninsula. It's much younger than the Frederick crater because it formed 65 million years ago. It wasn't quite as big as Frederick, but it killed the dinosaurs, so it's very famous. From this one, we have great examples of where the material from the impact was blasted out to. And we've been able to learn that an impact of this size can blast material across the whole planet. Every one of those dots on that map represents places where people have found material blasted out from the Yucatan Peninsula. We've even found fish skeletons that are full of fragments of the material launched out by the impact. Down there, that diagram in the bottom left, you can see in purple is the bones of the fish, and in green, that's the fragments shot out like buckshot by the impact. So let's come back to South Africa. This is right in the middle of the country. This is a little bit south of Johannesburg, which I haven't labeled on this map. But you can see in the middle that half circle of rocks that's lifted up, those hills right in the middle of that bullseye. That's the peak ring structure of the Frederick impact. The original diameter of that crater would have been about 300 kilometers. But we can't see it as clearly as we see the Chicxulub crater in Mexico or as we can see the Schrödinger crater on the moon. Because this impact happened 2 billion years ago, 2,000 million years ago. Now, there hasn't been any tectonic deformation. There haven't been any mountains lifted up to destroy this. But there has been a lot of erosion. So we don't see those molten rocks that would have been at the surface. We don't see those so clearly anymore. What we see instead is the deep architecture of the crater. So if we were to take a slice through the middle of the crater, right after it formed, it would have looked something like this. The rocks in the middle have lifted up, and covered with this molten material. But in the 2 billion years since the impact happened, all of that material on top has been eroded away. So we have to use the evidence that's down at the bottom in order to infer what was originally there. Now, if you go to Frederick today, the town of Frederick, then you might get lucky and have a chance to win a sheep. The town of Frederick is not very big, but the crater is named for it. Now, if you start looking at the rocks, then you'll find lots of evidence that all of these things actually happened. You'll find shatter cuts. These are places where shockwave from the impact went through the rocks and broke in this characteristic cone pattern. You'll also find what are called the granifier dikes. These are rocks that were completely melted by the impact and formed lines of rock that stretch across the ground and show us some of the hints of the strongest deformation that happened because of the impact. And then you have something called the pseudotactylite, which in this case you can see this climber is having a nice adventure rappelling down along these pseudotactylites. Now those are in a giant quarry. That whole hill is made out of granite, which is the pinkish rock that you see. But wherever you see the black lines cutting through that pink rock, that's places where friction from the impact that caused the rocks to slide against each other as they were making that journey all the way down 40 kilometers and up another 20 kilometers and settling back down. All the rubbing against each other that the rocks did. That's what's preserved in those black lines that cut through the rocks. And we can see that those are hugely incredible forces required to melt and destroy the granites in that pattern. Now, the Frederick impact, it is not only the biggest impact crater in the world, it's also one of the most important economically. Now in this diagram, this map, right in the middle of the map is the actual Frederick impact crater. And we can see all the rocks around it going out a distance of 300 kilometers that were all affected by the impact. But this map was not made to illustrate the impact. This map was made to illustrate where gold is mined out of the Witwatersrand Basin. See, all of those blue gold fields that are indicated, those are the big areas where mining of gold takes place. And none of those mines would have existed if it wasn't for the impact. When we look at the gold ore, it looks like this. You can see these mixed together types of rock where there are pebbles that used to be flowing down streams almost 3 billion years ago. And you can see all of these golden fragments inside. Now, all of those things that look like gold, that's actually fool's gold. But to confuse you, the gold is inside of the fool's gold. So it's actually not so foolish, fool's gold. Those rocks were deposited a long time ago, almost 3 billion years ago. But then they were buried deep below the earth. We never would have been able to find any of them if the impact hadn't brought them up to the surface. And there's been so much gold mined out of this, it's estimated that 1/3 of the gold that has ever been discovered anywhere in the world came out of this one basin. One impact crater gave us 1/3 of the gold in the world. So how did it do that? Well, in this diagram, the middle of the impact crater is on the right-hand side. And you can see how the rocks were lifted up. So all of that traveling that we saw, pushing the rocks down and then lifting them back up, that allowed these very deeply buried layers that had the gold to be brought up to the surface. So we can see when these were lifted up, it brought up these gold-bearing layers where the gold mines are located on the outer edge of the impact basin, but also in the middle of the impact. So when we go in the middle of the crater, we can find tunnels that people used to dig looking for gold. They abandoned most of these, which is nice, because now if you go around our ice, you can still enjoy all the hills that are there, because they didn't find much of the gold. But we find these same layers, these same types of rocks with exactly the same gold right in the middle of the Fredford Dome, which really confirms that it was the impact that brought this up. So Fredford is the largest impact structure in the world, but it's not nearly the only one. I talked a little bit about Swang near Pretoria, and I talked a little bit about Fredford, but there are impact structures all over Africa. Many have already been discovered. There's many that are still waiting to be discovered by anyone that's adventurous enough to go and check them out. In South Africa, we have 4 confirmed impact craters. The other 2 that I didn't talk about are deeply buried, but there's also impact craters in Namibia and Botswana. There's a lot of planetary science that exists in Africa, but a lot of it hasn't yet been really realized. So, one thing that I've been working on lately is the South African Planetary Institute for Exploring Nature with Technology. We have this strong natural history that's preserved in this country. We have many meteorites that have fallen on our land. We have rocks preserving some of the most interesting impact craters. We have some of the oldest evidence for life on Earth. We have evidence for some of the largest impacts that happened even before craters could be recorded. So what I'm aiming to do is to start sharing ways that we can be involved with planetary science. This is what SAPIENT is aiming to do, so that you can learn about programming and robotics and planetary science and the amazing natural history of our planet. And I think that is where we're going to leave off for today.